Hello, my name is Ivan Gotovchits and I'm a research scientist at Carnegie Mellon University, CMU. In this talk, we'll discuss Tagless-Final Style, TFS, and its application to program analysis. As our case study, we will use the CMU binary analysis platform, BAP. We split our talk into three main parts. In the first part, I will describe the context, BAP. In the next part, we will define the problem with which we will tackle. And the most interesting part, we'll gradually build the solution. Instead of a formal approach that prefers axiomatic exposition, we will stick to the example-driven, didactical one. We believe that our choice is justified. First of all, it suits better the format of the workshop. Second, there are plenty of Tagless-Final style papers that give formal but complete non-intuitional explanations. Okay, let's get started with BAP. What is the binary analysis platform? BAP is a set of utilities, tools, programs, libraries, and frameworks that interact with each other for the sole purpose, developing an understanding of what programs are doing. BAP understands many hardware architectures, including x86, ARM, MIPS, and PowerPC. Even more, we plan to add support for middle and high-level languages such as JVM and C, consequently turning BAP into a universal program analysis platform. BAP's implementation language is OCaml, but it's possible to write analysis and interact with BAP using Primus Lisp or common Lisp like DSL. It is also possible to use C and Python via C types bindings. However, using BAP generally doesn't require any programming skills thanks to the powerful command line interface. BAP uses a single intermediate language for representing programs compiled for different architectures. This language is precise and faithfully depicts each operation, including flag updates and various hidden effects not otherwise representable as changes to the CPU and memory state. To translate a program in a binary form into a program in the intermediate language, we need to know the semantics of the machine instructions. The semantics is specified either in a OCaml EDSL or in a Primus Lisp EDSL. Both representations are strongly typed and feature type inference. We can also leverage existing disassembling and decompilation frameworks to obtain semantics for free. For example, we use the NSA Ghidra, which translates binary instructions into P-code instructions, as the source of semantics. We achieve this by simply writing the semantics of P-code operations using Primus Lisp. BAP allows various intermediate representations of its language. Adding, modifying, or removing an IR doesn't require reinstallation or even recompilation. It is possible because BAP uses the plugin-based architecture with dependency injection. The modular design enables us to pack each feature of BAP as a separate APM package and give our users control over the desired feature set. As a bonus, dynamic linking lets us link LGPL code and still keep BAP MIT licensed. On the previous slide, we were talking about the current state of BAP. But it took BAP 16 years to mature to this point. The old ancestor of BAP is a C++ program called SM2C. It was the first, maybe naive attempt to decompile an assembly directly to C. We quickly realized that C is not suitable for the intermediate language, as it makes implicit too many things. We addressed the issue by encoding all side effects of a machine instruction in a specialized IL. It was our grandfather, Vine. This project is still alive and lives in the Berkeley BitBlaze project. The BAP was born then. It continues the tradition of Vine and also used intermediate language. BAP 0.x was an in-house development that was not publicly available. We removed all dependencies on proprietary or copyleft code and released the first beta version of BAP in 2014. After several iterations in 2016, we released the first stable version of BAP, BAP 1.0. We are proud to say that since 2016 we maintain the stability of the interface of BAP. Even in 2019, when we switched to the TaglessFinal Style, we preserved backward compatibility with the existing code. As of today, BAP has a vast and diverse user base. It features dozens of ready-to-use analysis, integrates with the modern state-of-the-art tools such as Ghidra or IDA Pro, and easy installable via OPAM. But let's go back to the timeline of BAP. We can see that from version to version we were switching intermediate languages. Each switch was painful, resulting in a hard fork of the platform, essentially letting the old version die and the user seek a new platform. In 2017, we were facing the same problem. We had to change our intermediate language as we needed support for new features. Floating point operations, instruction level parallelism, hardware parallelism is an incomplete list of features that were not representable in our current version of IL. We also were dreaming about accommodating bytecode and high-level runtimes, but we couldn't afford to lose our users by yet another hard fork. We had to find a solution to this problem. However, before solving a problem, we have to define it. We have a concrete list of requirements that constitute an ideal solution. The first requirement is extensibility. We want to be able to extend the language without breaking or modifying any existing code. But this is only one facet of extensibility. We also want our language to be independent of analysis. In other words, the language shall not dictate how to analyze itself. Together, these facets are known as the expression problem. But more commonly, we need another kind of flexibility than extensibility. Rather than extending the language, we often need to modify its representation to suit our needs. We may need to add hash constant or add to the language poster and precondition guards to leverage our weakest precondition analysis. Some of the tasks are easier to solve using a semi-graphical representation, while for others, syntax trees work better. In other words, we need to relinquish control over the language representation and give it to the users. That means that our language shall be abstract and allow multiple representations. Another requirement is that the prospective solution should be retrospective. That means that an implementation of this solution shall not require a complete rewrite of the existing code. We still want to maintain backward compatibility with the currently used language. We want static type guarantees in our language that prevent the construction of field type programs. Ideally, we want to employ the meta-language type system to enforce the well-formedness of the target language. Eliminating ill-formed programs on the construction phase also contributes to efficiency, as we could skip unreachable branches and focus our attention on real programs. As our output is a binary program, we'll build our intermediate representation by parsing that program. In addition, we want to store intermediate results for later processing and for distributing to other machines. That means that the proposed solution should enable serialization and deserialization of the program representation. Last but not least, our representation will be efficient in all senses of this word. It should have an efficient memory representation, both runtime and on disk. It should be portable across machines to enable parallel processing. The cost of abstractness should be zero or close to it. Finally, it should be easy to use and understand, which contributes to the efficiency of the language user. We have several constraints as well. First of all, the solution should fit into the vanilla OCaml type system. That means that we don't have type classes or module implicits. Another constraint is that we shall maintain close ties with the textbook abstractions. Many of our users are students who use BAP to learn program analysis, and they should be able to follow precisely the textbook algorithms. Finally, the solution shall play nicely with the BAP plugin-based architecture. It is well known that a plugin in OCaml can change the type environment of the host program, which is a heavy constraint. Let's start our search for the solution for what we have. The pre-2.0 BAP intermediate language called build had two representations, an abstract syntax tree and the semi-graphical representation in which control flow edges were made explicit. The AST representation uses OCaml algebraic data types, also known as variants. Maybe it is good enough? Many OCaml programmers will answer yes to this question. Just add a new variant and the compiler will gently guide you through the rest of your code where you need to address the newly added variant. To issue the abstraction requirement, we can decide on the set of possible representations that we need and write corresponding translators. This approach is valid and sometimes even optimal for monolithic projects that belong to a single authority. In other words, when you have access to all code which is affected by a change and have the right to modify it. Indeed, this approach is commonly seen in compilers and program analysis tools. However, history shows that it doesn't work for projects like BAP and other libraries and frameworks with a diverse and distributed user base. Every time we broke the interface, we had a lot of tools and analysis left behind. This situation is common for the academic community, where researchers, most commonly PhD students, develop tools until the paper is published and then abandon them. As a result, new researchers have to start their research from the beginning, which inhibits the progress. Okay, maybe turning it to an extensible variant or using some GEDT magic will help. Extensible variants might look like a solution to the expression problem. Indeed, adding a new branch will not break the existing code. We can even employ open recursion and a little bit of mutability to write extensible operations without modifying existing code. And adding GEDT will eschew ill-formed programs. But this solution doesn't match with the other requirements. First, it's not abstract. It is a concrete representation that doesn't permit change in implementation details like adding hash constant, for example. Some projects might relax this requirement, though. But let's move forward. Another problem with this solution is that extensible variants are not serializable. The same is true for GADT. Neither can survive a serialization-deserialization cycle. And writing analysis in the open recursion style turned to be non-intuitive and error-prone. Therefore, we have decided to abandon this approach. Of course, the expression problem is a well-researched topic with plenty of solutions. We excluded solutions that do not fit into OCaml and or are too convoluted, and ended up focusing on object algebras, also known as Tagless-Final Style, TFS. The approach is attractive in its simplicity. A language is a many-sorted algebraic signature, ID as a collection of sorts, types, and operators, functions, which perfectly maps to the OCaml signature. And the representation is an algebraic structure, or algebra, which perfectly maps to OCaml structures. We can see the signature as the syntax of the language, essentially a set of constructors, but in the functional form. To represent terms, TFS uses church encoding. A language term is a function that takes an algebra and returns the interpretation of this term in that algebra. In papers about TFS, they commonly use Haskell, where such encoding is implicit. In OCaml, we have to make it explicit and encode it as a function. And we immediately can see how type scopes complicate our life. To use a value, we have to extend its type scope by creating a local abstract type. It's tedious, especially when the number of sorts in our algebra becomes large. Another limitation of OCaml is that it can create only ground local types. In this example, we use multi-sorted algebras to model terms of two sorts, Boolean and integers. But we can't introduce a polymorphic type constructor on the expression level, as OCaml lacks higher-kinded polymorphism at that level. We can try to stick with ground types for our sorts, but this will lead to an explosion in the number of operators and won't work if the number of sorts is not finite. Another option is to use the high library. It gives us a way to represent higher-kinded polymorphism without functors, but I found that the resulting solution is still heavyweight. We also can't rely on functors for our terms, as a packed functor will have the same problem of escaping type. And remember that we need our language term to be a value, not a top-level definition, as we build terms from arbitrary input. The solution is to factor the type from the signatures and move to the global scope. It immediately resolves a lot of problems. We no longer need to write local type annotations and can fully encode multi-sorted languages, even with an infinite number of sorts. We still need to figure out how to encode the alpha T type in a way that preserves its abstractness. We know that abstract type have existential type, so we can finally employ extensible variants and GADT. Don't worry, we will solve the serialization problem later. We use an existential type to capture the algebra carrier set type. The sort is still captured, which is what we want. But there is still an issue with our representation. It's still church is still a function. Despite all our love for lambdas, we still prefer to use data types for representing program terms. Because we want to save them on disk, send over network, compare them, store them in sets, and otherwise use them as regular data types. The performance of the church encoding is also a big issue for us. Recall that we are not representing terms as EDSL, but parse them from the binary input. It is an inherently non-total and expensive process. We want to do it once and never repeat it. The solution is also on the surface. We can represent a function from algebra to the notations as a finite mapping indexed by algebras. In real applications, we always need all or some subset of representations at once. To compose several algebras into a single superalgebra, we define functor join. We perform pairwise join for each operation. And we can take a list of algebras and create a concrete algebra that we will use to create program terms. Now we have a term and we want to analyze it. First of all, we can use the good old initial style with pattern matching. For that, we can extract a concrete representation, like a term in BIL AST, analyze and transform it, and then inject it back. Yes, it's not extensible, but it enables the textbook style and backward compatibility. But what about the final style? Oleg Kiselyov's lectures and tutorials on TaglessFinal optimizations show that we can implement many transformations in TFS, including non-distributive analysis. In fact, after implementing a few algorithms in TFS, we can see an emerging patterns. Each implementation defines a specialized domain language. For that, we use common algebraic data types and pattern matching. The defined language is very tight and optimal for the task it solves. And what is valuable from the perspective of software engineering, the language is hidden under the abstraction barrier. In the end, we can claim that TFS facilitates the creation of new representations and does this without compromising modularity and extensibility. Another emerging pattern is the use of the state. Most, if not all, operations can benefit from the state, so it looks like a good idea if we would turn our universal term representation into a statementnet. Now the final piece of the puzzle. There is a particular kind of analysis that requires special treatment. We are talking about mutually recursive analysis, or more generally about the denotational semantics of non-structural recursive programs. The approach that relies on a state plus some specialized encoding is not sufficient here. We need to add fixed point computer to our statementnet. And to ensure termination, we need to impose an extra constraint on our algebras. They shall have the structure of a domain. Idea is to have an empty value and a join function. Besides, having join and empty makes it much easier to write the join functor that we wrote a couple of slides above. And in the end, we can pack all these ideas in a single library, which is independent of BAP and could be used by everyone. The library is called knowledge. Well, it is BAP knowledge, but ignore this namespace prefix. In addition to providing all abstractions that we described above, it also takes care of serialization. In the presence of GADT and extensible variants, it's a non-trivial but doable task. But this is a topic for another discussion. Thanks for listening, and please ask questions.